Hello everyone, myself Shruti Vyas and I'm going to talk about my research on cross-view video geolocalization. Our work GAMa cross-view video geolocalization have been accepted for publication at ECCV 2022 and the co-authors are Dr. Chen Chen and Dr. Mubarak Shah. What is geolocalization? Given an image or a video, we want to find out where it was captured. There are many applications of this problem, such as first respondents. We want to find out the source of an image or a video. There are two approaches to solve this problem. First is same view geolocalization, where the query and the gallery both are from the same view. In the second approach, that's cross-view geolocalization, the query is from the ground view and the gallery consists of the aerial images which are GPS labeled. In video geolocalization, there is some limited work in same view approach where they follow a frame by frame approach. However, in cross view, there is no reported work and no existing data set to do such type of work. Thus, we are solving the problem of geolocalization of videos, which has not been solved in cross view scenario. Given a video, the frames of a video or its trajectory can be outlined in a single aerial image. We want to make use of this relationship, and we propose a dataset, GAMa dataset for this problem, where GAMa stands for ground video to aerial image matching. In our problem formulation, the query is of ground video, and the gallery comprises of GPS labeled aerial images. The ground video is matched to the corresponding aerial image. If it's matched to the current, we get the correct GPS value. If it's matched to another aerial image, then we get an incorrect match. The motivation is to solve this problem at the video level rather than following a frame by frame approach. We want to make use of the context available with the video, that is geographical and temporal context. When a car or video move in the geographical region, we can see that there is a relation, temporal and geographical relation between the view received by the camera. We are proposing GAMa datasets, this dataset for this problem, which is the first video dataset for cross-view geolocalization. For this dataset, we have selected some videos from BDD 100K dataset. This is a sample of the video. And the corresponding aerial images were downloaded from Apple Maps at 19x magnification. We have aerial images at different scale. We have larger aerial regions which correspond to the video of 40 seconds. When we divide this larger aerial region into tiles of 7x7, we get our uncentered set of small aerial images. We call it uncentered set because the GPS label can be anywhere in the image. We also have a centered set where the GPS label is at the center of this small aerial image. For most of our experiments, we have used centered set because it's easier to work with. In our approach, we make use of these images at different scale and which helps in geolocalization of the video. The videos from BDD 100K dataset were selected based on their range in geographical range. So given this example, we have GPS labels for points x1 till xn. We have their latitude and longitude. So we use the range, that is the maximum of latitude or longitude range, to come up for a range for a given video. And we use the mu value from 0.001 to 0.004 to shortlist the video we want to keep in our data set. The selection is helps us remove the very slow moving videos or very fast moving videos from the set. Here we can see the distribution of number of samples at different mu values, and we can see that there are fewer samples which have mu values out of the range. In the test set also, we saw a similar distribution and use a similar mu values to select the videos. So this is some of the stats related to GAMa dataset. In the training, we have 45,000 videos, and the test set we have 6,500 videos. Corresponding to these videos, we have large aerial images. And based on the GPS labels available with the videos, we have corresponding clips. These clips are of 1 second each. And in the training set, we have 1.68 million clips. And in the test set, we have 243K clips. These are lots of videos and clips. So to reduce the training time, we have mostly used day videos in our experiments. Here we can see that the day videos are almost half of the full set. If we compare with the existing data sets for cross-view geolocalization, we can see that none of the existing data sets have videos. However, the proposed GAMa dataset has 51K ground videos. These datasets, the existing datasets, do have ground panorama, which has 360-degree view, which is unrealistic from point of view of video geolocalization, as videos usually have a limited field of view of around 70 degrees. As we saw before, we have aerial images at different scale. So the smaller aerial images have resolution of 256 x 256, and the larger aerial images, which correspond to the video, has a resolution of 1792 x 1792. GAMa dataset spans over multiple cities, as it's true for some of the existing datasets. In our proposed approach, we have two steps. First is clip level geolocalization, which is done using GAMaNet. The GAMaNet takes as input clip of half a second and matches it to the corresponding aerial image. Thus, from a video, we get a sequence of small aerial images. The sequence of small aerial images is input to the screening network for video level geolocalization. The screening network matches a sequence of small aerial images to a larger aerial region we saw before, which these larger aerial regions corresponds to video. Hence, we call it video level geolocalization. We make use of this video level geolocalization and update the gallery for GAMaNet in a hierarchical approach. Next, we search in the updated gallery using GAMaNet and arrive at our new matched aerial images corresponding to each clip. If we look at the network for GAMaNet, the GAMaNet has ground video encoder, which takes as input half a second clip. Ground video encoder has a 3D resonating backbone, and we get a feature vector corresponding to the video. The corresponding aerial image is encoded using an aerial image encoder, which has a 2D resonating backbone, and a transformer encoder to provide attention to the important features which corresponds to the video. Once we have the embeddings for video as well as aerial view, we apply contrastive loss considering these two samples as the positives. We try to bring these samples closer together in the feature space while pushing the other samples apart. These are some of these examples of clip level geolocalization. In the first row, we have frames of the query clip, and the second row, we have the ground truth. These are top 5 predictions by GAMaNet. The green bounding box here shows the correct prediction. Here we can see that there can be multiple correct predictions. This is because of the slow-moving cars or vehicles stopping at the red light. Thus, we have multiple images, aerial images, or clips corresponding to the same location. This is another example. Here also we have top 1 prediction, same as the ground truth. In these examples, we can see the last one is a failed case, since the ground truth is not in the top 5 predictions. But we can see that the top 1 prediction is visually quite similar to the ground truth. We make use of this relation for video level geolocalization and try to match a sequence of aerial images matched by GAMaNet to match them to the larger aerial region, which helps in video level geolocalization. Thus, the proposed screening network takes as input small sequence of small aerial images and encodes them using small aerial encoder. The small aerial encoder has a 2D resonating backbone and gives us a feature vector of 512 sites. The corresponding aerial image or larger aerial region is also encoded using larger aerial encoder, which is also 2D resonating backbone. The sequence of aerial images, when encoded using small aerial encoder, gives us embeddings corresponding to each image, and we average them to get a combined embedding for the whole sequence and match that to the larger embedding of the larger aerial region, applying the contrastive laws. These are our predictions for ground level, video level geolocalization, given these are the frames of the video. And in the second row, we have the ground truth. These are our top 5 predictions. Here, we can see that the top one is the correct prediction. We have 2 more examples here. If you closer look at the first example, you can see that part of the video is underground, like it's sort of a garage or something. Even though the part of the video is indoors, the sequence or the video before and after this part helps us in geolocalization of this whole video. Next, we make use of the video level predictions to update the gallery for GAMaNet. We take 1% top predictions of video level geolocalization and use them as gallery for GAMaNet. Later, in the hierarchical approach, we search in the updated gallery using GAMaNet and match these clips using the same network to their aerial image, corresponding aerial image, but in the new search space or limited search space, which helps in geolocalization. While we remove the gallery, update the gallery, we are removing some of the confusing samples, which makes it easier for GAMaNet to geolocalize. If we have a look at the qualitative results, the first row are the frames of the query clip. In the second row, we have top 5 predictions by combined model. Combined model is one of the ablations of GAMaNet where we don't have transformer encoder. When we use the proposed GAMaNet, we can see that the correct prediction is at 5th position. After using hierarchical approach and updating the gallery, we can see that the correct prediction of ground truth is pushed up to top 1 position. In this example as well, hierarchical approach helps improve geolocalization. Thus, we can see that using the hierarchical approach does helps in improve geolocalization by removing the confusing samples. However, there is a trade-off. When we reduce the gallery, there is some chance that the ground truth is lost in the part which is not selected, which makes it difficult for those samples to geolocalize. However, some of the samples have seen, many of the samples have seen an improvement in geolocalization when we use the hierarchical approach. Let's have a look at the quantitative results. In the first row, we have our image baseline based on the contrastive laws, where in this case, we only use a single frame of the clip and match it to the corresponding aerial image. When we use our video-based contrastive baseline, we can see that there is an improvement in the recall rate at all values. This improvement is because of the additional information or context available with the videos as compared to images. In our combined model, we see further improvement because of the various augmentations that bring viewing variance and provide hard negatives for better learning. With the proposed GAMaNet, when we use further improvement in the recall rate, and have a look at the hierarchical approach, we can see that there is an improvement at top 5 and top 1 recall rate. If we have a look at the top 1 values, a different threshold of 0.1, 0.2, 0.5, and 1 mile, we can see that as compared to GAMaNet, hierarchical approach provides better results, which implies that the top one prediction by hierarchical approach is closer to the ground truth as compared to GAMaNet. To conclude with, in this work, we are proposing the first dataset for cross-view video geolocalization, that is GAMa dataset, which has aerial images at different scale and long videos. We use or propose GAMaNet, which makes use of the geographical and contextual temporal context available with the videos and helps in clip-level geolocalization. We propose hierarchical approach to solve this problem by making use of the information available with the aerial images at different scale. We make use of the video level geolocalization to help improve the gallery for clip level geolocalization and improve the predictions using GAMaNet. In the future work, it will be a good strategy to use this approach along with same view geolocalization to further improve the recall. Our code and dataset is available at this link. Thank you for your attention. Have a great conference.